Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We were discussing aqueous complexation in our previous lecture and we are going to continue discussing aqueous complexation in this lecture. So, in previous lecture we were discussing how we form inner complexes and outer complex spheres and we came across a term called ligands. Okay, so, as I have already said, ligands, they are either an anion or it can be a neutral molecule. Often enough amount of organic ligands can be there. There can be different kinds of proteins, they can be different types of acids. For instance, humic acid, fulvic acids are very commonly found when their organic matter is degrading. So, a variety of proteins, carbohydrates, everything exists in solution, right, in natural waters. So, organic ligands are also their variety, their molecular diverse kind of molecular structures will be more as compared to inorganic compounds. Inorganic compounds we often can predict a lot of complexes that we often encounter, but organic ligands their numbers can be really large. So, today in this lecture we will see metal cation ligand relations in complex formation and we are going to see adsorption. Metal cations are appreciably smaller than the ligands with which they form complexes, of course, because as I said that the ligands, they can be molecules, okay, and often they will be organic molecules. Now, organic molecules, by the definition of which you will understand, it will have a structure will be like something with a C, there will be H, there will be O, and it can have some X, and with this it will have some maybe nitrogen, there can be sulfur, or it can be very complex kind of molecules. Okay. So, in comparison to this, our simple metal cation, say for instance sodium or for instance calcium, okay, their size will be very small, right. So, due to their position, due to their charge around that is surrounding with them, they can associate with many different types of ligands. Okay. So, typically the absolute charge of metal cations exceeds that of the coordinating ligands. For example, again as I said, say suppose uranium is existing as +6, okay, it is soluble as +6, okay. Uranium is most soluble in its highest oxidation state, that is +6 state. So, a ligand may maximum have +2 -2 if it has to form a complex with uranium. So, there can be 3 such ligand molecules that will form complex with uranium. Okay. So, there will be 3 such X molecules. Okay. So, there how many ligands will coordinate with a particular cation, all this controls the coordination number. Okay. So, the maximum possible number of ligands surrounding or bonded to a given cation in a complex is something which we call the coordination number. Okay. So, coordination number is always very specific with respect to the ligand. Okay. It is always very specific with respect to the ligand. And because this is very long range. Why long range? Because this is this is forming multiple bonds. So, the uranium is forming bonds with 3 other ligands. Their position is such that they will be in like a long range in terms of atomic scale. So, therefore, their nature will be Coulombic forces. Okay. So, it will be the Coulombic forces of attraction. So, this is not a covalent bond, this is not a very strong bond. Okay. These are mostly Coulombic forces and they are, their stability depends on this coordination number. Okay. So, the maximum observed, the more often observed coordination number is either 4 and 6. Why? Because they are very stable. Okay. In this coordination number, they can be very stable. Lower coordination number, they might often be competed with. So, they may be not be very stable. Similarly, higher coordination number may also not be extremely favorable. Okay. Again, these are extremely specific to the cation and the ligand pairing that we are talking about. For certain, it will always be the higher coordination numbers are more stable, for certain others it may not. So, it depends always on the ion pairs that you are talking about, and I mean ion and ligand pair that you are talking about. So, you can have a variety of monodentate. So, what do you mean by monodentate? Only one available charge is there, right, or it can be bidentate ligands, okay, or it can be tridentate ligands. So, as you see, as the as the coordination number is increasing of these, these are more complex ligands. Okay. So, citrate, okay, nitriloacetate, these are more complex molecules that will form under very specific conditions, and due to the presence of more organic matter, okay, certain kinds of molecules they will only be available. For example, this EDTA, okay, this is very specific kind of molecule, right. So, the maximum observed number of coordinating ligands in complexes rarely exists either 3 or 4, okay, less than a cation's maximum possible coordination. Okay. So, when a ligand is, so if we are finding the CN number for a cation, that will always be greater than the CN number of the ligand. Okay. That means a cation can form multiple complex with multiple ligands, but the ligand will have lesser choices. So, it will hardly ever exceed other than 3 or 4. Okay. So, ligands, their structure does not allow more complexation, their structure does not allow more complexation, except for aquacation complexes in which the water molecules occupy all possible coordination sites. Then it can have the typical 6 site number. Okay. So, except for the aquacation, in that case I am considering the water as a ligand itself, alright. So, except in that cation cases, it is rarely exceeding 3 or 4. Okay. So, except for aquacation complexes, ligands they generally have 3 to 4 complexes, 3 to 4, that the coordination number is maximum up to 3 to 4. Okay. And in natural waters, stabilization with high number of ligands is very difficult. So, for example, if a molecule is attached to more number of ligands and that ligand is again attached to other different kind of molecules, then that big complex, the stability of that big complex, the bonds becomes very weak. You remember, these are long range Coulombic forces. Okay. So, their bond length, okay, can become the factor for their instability. Okay. So, that becomes, then it becomes very difficult, and often they can also face competition. So, ligands they will compete against other ligands, okay, or they will compete with the water molecules to get in. If it is having a very strong ionic potential, then it might go and sit in the inner sphere. Okay. So, that depends on what is the ligand structure. So, when we come to structure, we talk about in terms of geometric arrangement, right. It depends on the geometric arrangement. So, if it is a plane equilateral triangle, So, it is a very plain equilateral triangle. The formula is basically Bx3, right. So, it is a plain equilateral triangle. There will be a cation in the middle surrounded by 3 oxygen atoms, or similar formula, but another arrangement is a pyramidal arrangement, regular trigonal pyramidal arrangement. Okay. So, the oxygen is at the corners of the equilateral triangle here, but the central atom will be above this plane. Okay. So, this is the so this is oxygen, this is oxygen, this is oxygen in one plane, and this is another, the cation is sitting here. Okay, this is above the plane. So, if you look in 3D, this is like a pyramid. Okay, so this is the pyramidal shape, or it could be the tetrahedral shape. So, tetrahedral is here the base is triangle, there the base will be square, right. So, there the base will be square. So, it is a regular tetrahedral which is the most stable ligand group. Okay. So, these are very stable, the BX4 group, and these are some of the few examples that we often see. For instance, this is a very stable aqua complex, that is the silica OH whole 4 complex. Okay. Almost all of silica exists in this particular complex form. Okay. It is extremely stable form. Okay. Otherwise, it can be a distorted tetrahedron. So, this is again a very distorted, the same formula, but it will be a distorted figure. So, again it will be formed with different charges, they will be having different charges and their ionic potential will be different. So, these are atoms with larger atomic radii, right. Or there can be another arrangement extremely common, that is a spherical. Okay. The spherical arrangement is the most common arrangement. Okay. So, here you have Bxn and there can be this n depends the coordination number, n is the coordination number. So, some general observations on complexation. Okay. The stability of complexes increases with the increasing charge and or decreasing radius of the cation, so that the ionic potential is strong. So, either the charge has to increase or the radius of the cations has to decrease, okay, for a given ligand or of ligands for a given cation. Okay. So, either you are calculating it for a particular cation based on a given ligand, or if you are calculating for a ligand based on a given cation. Okay. Ion pairs or outer sphere complexes, they are weak and they are electrostatically bonded. So, these are called the ion pairs. Okay. They are outer sphere complexes. Inner sphere complexes, they involved or they develop covalent bonding between the cation and the ligand, and they are much stronger than the outer sphere complexes. Okay. Cations and ligands that form strong complexes, they will tend to form minerals with very low solubilities. That means, they will hardly ever precipitate. They will remain like that because their complex is so strong. Why will they precipitate, right? So, they will form minerals which are with low solubility. Complexing tends to increase the solubility of minerals that contain the species being complexed. Okay. So, complexing tend to increase the solubility, the minerals will become more soluble, and if the species is there, then those particular species that will increase the solubility. Okay. Complexing of a species may also enhance or inhibit its adsorption and usually affect its toxicity and bioavailability. This is an extremely important, you can mark 3 times as a very important application of understanding complex formation and speciation, is that complexation will either enhance the absorption and make it more bioavailable, or it will inhibit its adsorption and thereby reduce its bioavailability. What do I mean by that? For example, a particular plant, okay, say suppose it needs calcium, okay, it needs calcium. Now, if it is in its calcium SO4 0 form, that is in an ionic pair form, as it has formed a complex now, okay, it's formed a aqua complex now. For that plant species, in the root where it was going to attract it, where it was going to adsorb the calcium, that particular area, okay, for adsorption is very specific for calcium. It will not favor calcium complex, okay. So, this will inhibit the bioavailability. This complex formation will inhibit the uptake of calcium, right. This is because the plants, they have specific sizes to which, through which they absorb, and that will be translocated to their upper, from the roots to the shoot region and leaf region and all that, okay. In animals, in plants, it depends on the receptors, right. So, the receptors will be suitable for only a particular size. If it is a complex, then their size will be a major inhibition towards their uptake, or vice versa. If it is too tiny and the complex is very suitable for that, the transporter to transport that size, then it can enhance the bioavailability, okay. So, forming complexes is therefore controls the toxicity of particular metals and also the bioavailability of important metals. Also, the more saline a water, the more ions in it, especially the multivalent ions, and they will all exist as complexes, okay. So, I will show you the calculation where the saline water is so ionic, okay. There will be enough competition from sodium as a positive cation and chloride as an anion. So, they will, due to the availability and due to another effect, which will soon we will learn that, they will always exist as complexes. And therefore, the more saline a water, the more the solubles tend to be in, because of this complex formation and activity coefficient effect. Activity coefficient effect is something different, okay. But the point is that in high saline water, these minerals, they will tend to be more in their complex form, okay, and therefore, the solubility of the minerals will be increased. So, let us see what is activity, right. Activity, we came across this term when we were doing thermodynamics. We discussed a lot about activity, and in this particular we are just going to try to understand how and why is activity happening, okay. So, ions in solution, they are always interacting. So, that is the basis of our complex formation. At low concentrations, if the concentration of a particular element is extremely low, that is it is very dilute, okay, or with a very low salt concentration, it is a fresh water, okay, it is a very dilute water, then these interactions can possibly be ignored. Okay. That means you say it is a very dilute water, the activity of this water will be very similar to that of the concentration. So, that I will there will be negligible changes, and therefore, all that is there in the concentration which is so low, I consider it as equal as the activity, okay, or the so then you can easily proceed with your further calculations. But if the salinity is high, or if it is a very concentrated solution, then the ions start behaving very differently. They start behaving as if they are less concentrated than they really is. For example, if it is a 1 molar solution, it will start behaving as if it is a 0.99 molar solution. Okay, it will start behaving as if there is some less concentration, a slightly less, not a lot, but there is a slightly less. Okay. So, this is what we called activity, is where we are defining a term which is called the effective concentration. Okay. So, when we are when we were discussing equilibrium constants and we calculated that from the free energy of the reaction, that was the del G R 0, we expressed it in terms of this, we want to express it in terms of this effective concentration, which is called the activity for a solution. And this is the concentration that is available for any reaction. Okay. In infinitely dilute solutions, the ionic concentrations, the ionic interactions, they can be ignored, and therefore, it is an ideal solution and the activity is equal to the concentration. But in most cases, and especially for seawater, the activity is less than the concentration, and therefore, we are dealing with non-ideal solutions. But what is the reason for this? What is the reason that we see we make 1 molar, but we find 0.99 in practical sense? Why is that? This is because of these two important phenomena, these two important processes, and one is electrostatic interaction and the other is ion complexing or specific interaction. So, first is of electrostatic interaction, other is the ion complexing or specific interaction. What is electrostatic interaction? Let us look at it. Okay. When we talk about electrostatic interaction, there is a lot of ions in the background, right. We are talking about a natural solution. In this natural solution, there can be multiple types of ions that will shield the charge and the interactions between the ions. Okay. So, let us take an example to make you understand better. For that, let us take calcium and sulphate in water. Okay. So, the tendency of calcium and sulphate ions to hydrate induces shielding. So, if you have calcium, you will have this water molecules around it. Similarly, if you have sulphate, you will have the water molecules arranged around it. Okay. This will affect the ability of calcium and sulphate to meet and react. Okay. That means, these extra components will act as shields that will prevent the interaction between the ions. Okay. This will prevent the interaction of the ions. Now, in more saline water, where we have further high concentration of two extremely reactive ions, that is sodium and chloride, they will get attracted towards oppositely charged and they will effectively increase the amount of electrostatic shielding, right. So, these are very high ionic potential. Why? Because their atomic radius is very small. So, due to which they will fit in wherever possible in this structure. for the same, for the sulphate also they will try to fit in wherever possible in the structure, and they will increase the shielding effect. Okay. So, therefore, calcium sulphate remains dissolved and it will remain more soluble in sea water due to the presence of chlorine and sodium, okay, as compared to fresh water. It is not very easy to precipitate gypsum out of sea water. So, it is because of these shielding effects that we see such non-ideal solutions. Okay. And the ions with higher charge, they are more effective than ions with the lower charge. So, instead of sodium, if there would have been a stronger higher charged an ion here, cation here, then the effect would have been more stronger. Okay. So, now thing with sodium is that it has an extremely small ionic radii. So, you always have to see the one with the small atomic radii, okay, the atomic radii is important, and also the charge has to be important. Okay. So, either it has to have an extremely high charge, so +6 or +4 charge, something like that, or it has to be an atom with a very small atomic radii, okay, small atomic radii. Let us see how we calculate ionic strength. What do we mean by how to calculate the ionic strength of a solution? Okay. Now, ionic strength, if you want to calculate the ionic strength of a solution, because based on the ionic strength the electrostatic forces will be active. We can understand the electrostatic forces based on this ionic strength of that particular solution. So, what we do, we are going to use this formula, that is I is equal to half of summation of Mi into Zi square. What is Mi? Mi is the molar concentration and Zi is the charge of that particular ion to the power whole square, okay, to the power of 2. So, what do we do? For instance, if we have sea water, all the major cations and the major anions has been provided, okay, in molar concentrations. So, we are going to calculate. So, molar concentration of sodium into its charge to the power of 2 plus molar concentration of magnesium into its charge, that is 2 to the power of 2. Similar for calcium, similar for potassium, for chloride, for sulphate and for bicarbonate. So, I come to this value which is 0.72 mole per kg. Okay. The ionic strength has concentration units, okay, it is the same unit as that of concentration, okay, that is mole per kg. Now, let us compare it with lake water. Lake water you can easily see the difference. So, it is concentration is very low, right. So, the ionic strength of sea water is 500 times more than that of fresh water. So, therefore, we cannot neglect activity, we cannot neglect complex formation in sea water. Okay. Also extremely important is that here charge is having a whole square factor, right. So, a higher charged ion will contribute more to the ionic strength as compared to the lower charged ions. Okay. So, if this is sulphate, okay, sulphate will contribute, even though it is significantly lower than chloride, it will still contribute high, I mean not more than chloride here given the values, but its contribution will be high because of this square term. Okay. So, here the molar concentration will be multiplied by this 2 whole square. So, it will be 4 times than that of chloride. Okay. Let us come to this term called adsorption. Now, complexation, okay, controls a lot of something of a process that we call adsorption. Okay. Adsorption is simply there will be a substance, there will be a surface, and there will be defects here due to which there might be charged particles that become exposed here. So, the positive metal ions they can start getting absorbed here, okay, different metal ions they can start getting absorbed in the different surface area. Now, this process can have three kind of due to three kind of interaction. One is first thing of course the surface complex formation, that means due to the bonding kind of thing between the metal and the kind of charge particle that is here, okay, whether this is forming, how strong bond this forms with the adsorbed particles, okay, and this is extremely similar to complex formation, okay. So, electrostatic forces, Coulombic forces, how strong they are between this across the surface depends on that depends the adsorption, okay. Otherwise there will be electrostatic interactions, okay. So, what is it? They are electrically charged. So, due to this kinks and all that, kinks and surface structure, there will be some kind of missing charge, okay, a particular charge will be missing, due to which there will be an electrically charged surface, okay, and due to which there will be attraction and a cation can start getting replaced here. It can get inside the physical structure or it can be adsorbed. So, basically that kind of adsorption. Okay. This electrostatic force which is effective over greater distance than purely chemical forces affects surface complex formation and they loosely bind other ions to the surface. So, it can also bind other ions to the surface. And for when we are talking about solutions, we think that a solution will always maintain a electrical neutrality. For example, if you are standing near a lake or you are standing near a river, you do not feel any kind of electrostatic force. So, your head is not getting towards the water or it's. So, water is generally electrical neutral. So, it is electrically neutral, but surfaces are not. We cannot make assumption that a surface will always be electrically neutral. It's always depends on the kind of structure of that surface, and often we see that they due to the dislocations and misfigured structures, they will have some charged surfaces. Another kind of attraction is the hydrophobic adsorption. Hydrophobic, that means it fears water. So, this is mostly we see for lipids, that is organic substances, that is they are not soluble in water, okay. They will not be soluble in water, therefore, what they will do is they will get adsorbed to the surfaces, okay. Due to the repulsion from water, they will get stick to any surface that they can stick to, okay. So, therefore, these are the three kinds of adsorption processes, and this is just to show the complex types of structures that one can find, where it can be metal. So, this is general structure where a metal has a hydroxide, and maybe this metal will start replacing this H plus and this will form adsorption, this will be the adsorbed result, or it will this entire OH will get replaced by a ligand, or it will just go on forming. If this is higher charged metal, this will go on forming a lengthier, it will also bind few ligands. Okay. Same thing for the ligand also, if the ligand has a higher charge, then it will go on binding the metals, and it can be bidentate, tridentate, okay, it can be multiple dentates. Okay. So, these structure, so adsorption is a very surface dependent process. What kind of surface is this? What kind of ions are there at the surface? How much charge it is? Okay, that is how adsorption reactions are controlled. And if you are looking at saline waters, what happens is often this higher electrostatic potentials, so sodium, they will often compete. Okay, they will often replace the metal ion here, and they will themselves get the, so suppose here adsorbed to a particular clay mineral was this big metal cation. Okay, let us call it X. Okay. And here you are a saline water. So, here is my lot of sodium, lot of sodium is there. Okay, lot of sodium is there. So, what will happen is sodium being a very strong cation, it will easily replace this one, and it will start getting attached here because of its higher ionic potential. It will get attached here, it will replace this. So, there is always a fight for adsorption sites. Okay. There is always a fight for adsorption sites, and therefore, in saline water you will see suddenly the concentration of adsorbed metals have suddenly increased. Why? Because the sodium is replacing all the larger cations, and opposite also there chloride can also sometimes replace some of the larger ligands. Okay. So, this is always happening in saline water. Now, with this I will come to an end to this lecture, and in the next lecture we are going to see how we calculate speciation. We are going to look into one particular software, and I am going to show you how to use that software. It is a very simple user friendly software, and I think anybody can do that. With this I end today's lecture. See you in next lecture. Thank you.